Hello, Algebra 2 students. This is a lecture on graphing simple rational functions. This is also our introduction to rational functions as a whole. Let's go ahead and get started. So what is a rational function? Well, rational functions are one of those things that, in my mind, some mathematician was getting bored of whatever he was studying, and it was like, let's try to make a new function. And so we've already studied polynomials, right? We've studied linear, cubics, quadratics, quartics, all these things. What if we took one of these types of functions and divided it by another type of polynomial, another one of these functions? What would it make? And what we actually get is this whole other world of types of graphs, and we call them all rational functions. The most simple rational function would be y equals 1 over x. Basically, it's a constant polynomial, just a number, divided by a linear polynomial, just x. And some of these are actually pretty wild, and they vary a lot. We're going to be looking at a lot of different types of rational functions in these next two sections where we're graphing rational functions. And today we're looking at basically just the more simple ones. And so this graph, as you guys can see here, is this line here and this line here. It's actually got two different parts to it, two different sections. And it also has two different asymptotes. There is a vertical asymptote right here, and there is a horizontal asymptote right here. The vertical asymptote's at x equals 0, and the y asymptote is at y equals 0. Like I said, it's got two branches. One of them goes like this. Remember, asymptotes are imaginary lines that our graph approaches but never reaches. So this red line, the actual graph of the function, is getting closer and closer to this asymptote here. Then it goes this direction, it gets closer and closer to the asymptote here. We have a second branch up here, starting, going this direction, and then this way. Cool. So you guys are going to be expected to tell me what the asymptotes are for these types of functions. And you're also going to have to be telling me what the domain and range is for these types of functions. So chapter 8 is where I actually introduce a new type of notation for telling me the domain and range. Our graph, of course, is in red here. It does not have an unrestricted domain. There is a certain restriction on it. This graph, if you guys can process this with me, it goes to the left forever, right? This graph continues this way forever. However, it doesn't go this direction forever, from here at least. It goes, and because there's an asymptote here, remember, asymptotes are things that the graph approaches but never reaches. And so this branch here is getting closer and closer to the asymptote at 0, and then it never actually gets to 0. It just gets closer and closer to it forever. And then starting up here, once again, it gets close to it forever, but it never actually gets to 0. Never actually gets to the x value of 0. And if we're reasoning through this, we can actually figure out why 0 is not in the domain. Remember, this is the function that we're graphing, y equals 1 over x. And one of our main rules in math, one of our rules we've known forever, is that you're not allowed to divide by 0. If you do 1 divided by 0, of course you're going to get a divide by 0 error. It's not something you're allowed to do. And so 0 is not a value you're allowed to plug in for x because it would give you an error. Therefore, it's not in the domain. The domain of this function would be all real numbers except for 0. And we're actually going to learn a new way to say that. As you think about the domain, this goes forever to the left. And so the smallest point in its domain, we're going to say, is negative infinity. Okay? I don't want that extra parentheses. The domain would be starting at negative infinity, and then where does it stop existing? So it goes forever to the left, and then it's existing, moving to the right, keeps going to the right. It stops existing at 0. And so we'll put a 0 there and a soft parentheses. Soft parentheses are like greater than signs or less than signs, and they indicate that you do not include the endpoints. And technically, we can never get to infinity or negative infinity, so infinity will always get a soft parenthesis. And we want to go to the x value of 0, but not include 0. And so we use a soft parenthesis because the domain doesn't actually exist at 0. Once we get beyond 0, though, the U means and you guys are going to get used to this here. So once we get to this side of 0, it starts existing again, and then it goes forever to infinity. And so this is the notation that we're going to be starting to use in Chapter 8. I'm not going to give you full points for doing domain and range the way that we've been doing it with like inequality signs and stuff. This is called interval notation, and it's going to be much more useful as we look into the more complicated functions in Chapter 8. So its domain goes from negative infinity to 0, but doesn't include 0. And it picks up again at 0 and goes to infinity. Now let's look at the range. The range is the y values that this graph achieves, and this graph goes down forever, right? Right over here, it's going down forever. And then we're working our way up, but it doesn't actually get to the y value of 0, right? Because there's an asymptote there. This line here, this branch, is getting closer and closer to 0, but never actually getting there. So its range starts at negative infinity and goes to 0, but doesn't include 0, because this line is getting closer and closer to a y value of 0, but never actually reaches it. And we pick up again at 0 over here, and then we work our way up forever. So 0 to positive infinity would be also the range. It's not always going to be the case for all of these functions, but for the more basic ones, that will be the case. So let's go ahead and look at how we would graph this. This graph is very similar to the graph of y equals x, but we'll still play around with it. So we have 3 divided by x. We can graph this. You're going to see that it looks very similar. My expectation for you guys is that you are going to draw the asymptotes in and tell me what the asymptotes are, and then find the domain and range. So for this particular graph, 3 over x, we are still having a vertical asymptote at x equals 0. Because there's a vertical line at 0 where the graph never reaches, it just approaches. And we also have a horizontal asymptote at the line y equals 0. So here's our vertical asymptote, and here is our horizontal asymptote at y equals 0. Once you have your asymptotes filled in, you're just going to go to the table and you're going to plot some points. So at negative 3, it's positive 1. At negative 1. At negative 2, it's negative 1.5. And at 1, it's positive 3. And at 2, it's 1.5. And at 3, it's 1. Okay, so let's plot this guy. So we can see it's doing this whole number. And it goes out here, and it approaches that line. And then we also have one here at negative 1. It's negative 3. So this one here, we go like this. Very exciting. Like I said, it's very similar to the graph y equals 1 divided by x. We're going to see more complicated versions of this, but you can see y equals 1 divided by x was just a little bit tighter to the origin, and 3 divided by x was just a little bit more away from the origin. So we would also be expected to identify the domain and the range of this function, and I bet you guys could guess it. This graph goes forever to the left, and then as you work this way, it does not get to the asymptote, right? Because that's the line that the graph is approaching but never reaching. So it starts at negative infinity and goes to 0, but it doesn't actually get to 0 because it's an asymptote. And we pick up again at 0 and go to infinity, right? So all x values exist. This direction, they exist. Nothing exists at x value of 0 on this line. But then once you get above 0, it starts existing again and goes forever that direction. The range, on the other hand, would go down forever, judging by the blue line. And then, once again, it goes up, stops existing at 0, so negative infinity to 0, and 0 to infinity. So that's as basic of a rational function as we can get. We are going to see some more complicated versions of this, and it should kind of ring a bell. We have, ta-da, AH and K. And we've seen AH and K. I promise that it's going to be something that keeps coming back. We know that K is our vertical shift, and it happens the way that we think it will. Right? That's review for us. We know that H is our horizontal shift, and horizontal shifts happen the opposite way that we think it will. And A, as we saw when we compared these two examples, A is adjusting how steep our graph is increasing or decreasing. So my expectation for you guys, when you guys notice this form, and you're going to see different forms, so it's not always going to be in this form, but when you see this form of AH and K, you identify that, and you are able to come up with where the asymptotes are going to be in your head based off of this form. And then once you do that, you're going to plot the points using your calculator and graph it accordingly. So here we have one of those examples. You guys should be able to look at this and say, hey, this is an AH and K problem. This is a translation problem. We know that +3 at the end of our function is our vertical shift, and it's going to shift the way that we think it would. So +3 at the end is going to shift up 3. And -2 on the inside, that's our horizontal shift. And we know minus, I would think, would move to the left, but it actually moves to the right too. And so all of our asymptotes would have occurred at 0 and 0. However, they're going to be shifted now according to what I just wrote. Okay, our asymptotes are going to be shifted up 3 and to the right 2. So before I would have had an asymptote here. I'll draw these in blue and then probably erase them or something. And an asymptote here. But now both of them are going to be shifted up 3. Well, shifting a vertical line up 3 does absolutely nothing. So really what we want to focus on is, hey, we're shifting this asymptote up 3. It's not going to be at 0, 0 anymore. It's going to be at 3. And we're also going to shift both of our asymptotes to the right 2. Well, shifting this line to the right 2 does nothing. But shifting this one to the right 2, that's not fun. Shifting this one to the right 2 will absolutely do something. Put it right about there. We'll call that good. So there's our new asymptotes. We have a vertical line. Vertical lines are written x equals. We have a vertical asymptote at x equals 2 because this is the line where the x values are always 2. And we have a horizontal asymptote at y equals 3. From here, we can go ahead and graph this using our calculators. Really important point to point out. When you type this one into your calculator, you're going to need parentheses around it. You need a way to indicate, hey, we're doing -4 divided by x minus 2, not just -4 divided by x. So -4 divided by x minus 2, like that, plus 3. Now, when we graph this, it should line up with our asymptotes, and it does appear to line up with our asymptotes, right? Our graph is shifted up from what it used to be and to the right, which is a good sign. It means we're probably doing something right. From here, you're going to push second and then table. We have some points here, -3, 3.8. That's about right there. -2, 4, 0, 5, and 1, 7. Cool. 3, -1, 4, 1, 5, 1.67. Did I mention this is like my favorite chapter? I think these are fun. So anyway, here's our graph. It goes like this. Getting closer and closer to the asymptotes. We have the same thing over here. Getting closer and closer to the asymptotes. The only thing that's going to be left that would be expected of you guys to do is come up with the domain and the range. So the domain, before we kept getting, it goes from -infinity to 0, but our graph actually does exist at 0. Right here it exists. So it's not going to be -infinity to 0. It's actually going to be -infinity to wherever this asymptote is occurring at, right? Because this is the x value that doesn't exist. This is the x value that the graph is approaching but never reaching. And it also might help to think, okay, what am I not allowed to plug in for x? And I'm not allowed to plug in 2 because that would give me that divide by 0 error. So its domain is from negative infinity to positive 2. Because, once again, this graph is existing, doesn't exist at 2, but then it picks up after we hit 2 and goes again forever. So its domain is going to be negative infinity to 2, and remember that U symbol, it stands for the union of, or and, you can kind of replace it with, 2 to infinity. These are not ordered pairs like we're used to seeing them as, but they are written like this, and it looks like it. All right, let's just come up with the range, and then we'll be done with this problem. This graph also goes down forever, and it comes up, it stops existing at whatever the asymptote is. And our asymptote is existing at positive 3 on the y's. So this is going to go from negative infinity to positive 3, and then it picks up again after 3 and goes up forever. 3 to infinity. Go ahead and pause it here, try this one, see how you do. I'm going to whip through it really quickly. Minus 2 at the end shifts down 2. Minus 3 on the inside I would think would shift left, but it actually shifts right 3. So this graph is going to have asymptotes down 2 and to the right 3. Boom, 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 boom. From here, you'd go ahead and you would type it into your calculator, remembering to put this in parentheses, your denominator. 1 divided by x minus 3 minus 2. We can push graph there, it'll graph it for us. We can push second table and get the actual points. It's going to look like this, we know, right? So you are not allowed to do this, but I'm going to. There, and something like that. This actually probably should have been tighter, but anyway, that's why you get the points. So our vertical asymptote is at x equals 3. Our horizontal asymptote is at y equals 2. Our domain goes from negative infinity all the way to positive 3, and then picks up again at 3 and goes to infinity. The range, on the other hand, goes down forever, but stops existing at negative 2. Negative infinity to negative 2, and then picks up again at negative 2 and goes to infinity. This is our second type of simple rational function that we're studying in section 8.2. We just had these really basic ones that only had a over x, y equals a over x, it could be written as. And then now we're looking at the type that has the a, h, and k. Would be written like this with a, h, and k filled in. And then the third type of simple rational function that we're going to look at would be when we have a linear function, something like mx plus b, being divided by something like mx plus b again. We have a linear function divided by a linear function. And it's not going to work to think of linear function divided by a linear function as a, h, and k. It just won't work that way. We have to think of it as something different, and here's going to be the pattern for you to do that. So if we have a linear function divided by a linear function, we are going to first find its horizontal asymptote. And its horizontal asymptote is going to occur at y equals a divided by c. We can see a and c up here. Just divide these things by each other, and we have our horizontal asymptote. The vertical asymptote is going to occur at whatever negative d over c is. I don't like to think of it that way, but this is the way the book refers to it. I prefer to think of it as whatever makes your denominator 0. Okay, we know that the vertical asymptote is occurring because we're dividing by 0, and that's the thing we're not allowed to do. So whatever makes my denominator 0 is going to be my vertical asymptote. So let's look at an example of this. We have the line y equals 2x plus 1 divided by 4x minus 8. Let's start out by first recognizing, hey, mx plus b, right? That's what this looks like. This is a linear function divided by a linear function. Aha, that means I got to follow these set of rules right here. The horizontal asymptote is going to occur at whatever a divided by c is. And in case we're forgetting, this is where a and c are. A and c are going to be the coefficients of x. So 2 over 4, I would give you partial credit for that because we are expected to reduce that to 1/2. So the horizontal asymptote is occurring at y equals 1/2. The horizontal line is occurring at 1/2. The vertical asymptote is occurring at whatever makes my denominator 0. Sometimes that's easy to find, sometimes it's not. In the event that it's not, just set it equal to 0 and solve it. Set your denominator equal to 0 and solve your denominator. We'd add 8 and divide by 2, and that's where our vertical asymptote is going to occur. So from here, once you have your asymptotes drawn in, we can go ahead and type it into our calculator. Now, if you just type it in like this, which I'm going to get some of, I know, 2x plus 1 divided by, this is wrong, right? That's what I'm telling you. Your calculator is only going to do 1 divided by 4. That's not what we want. We want 2x plus 1 being all divided by 4x minus 8. So make sure you type it in with parentheses around your numerator and parentheses around your denominator. And then we'll be able to see the graph, and it should line up with our asymptotes. We can push second table and get the points. I'll actually do that for this one. It looks like 1, negative 0.75. Well, they're very, very close to the asymptotes here. What about 3? 3 is 1.75, and then 4 is 1.125, and then 5. Okay, so here's what our graph is looking like. Boom. And this one's just real tight to the asymptote again. So our last step would be to come up with the domain and the range for this function. The domain, this graph is existing starting at negative infinity and working its way to the vertical asymptote. So it goes from negative infinity to positive 2 because it can't exist at the vertical asymptote. And then it picks up again at 2 and goes to infinity. The range, once again, is starting from negative infinity, working its way upward, and stops existing at 1/2 this time. Negative infinity to 1/2. And then it picks up again at the other side of 1/2 and goes to infinity. Let's do one more of these examples. You guys go ahead and pause it and try it on your own, and then we'll look through it together. Your horizontal asymptote, keep in mind, is the coefficients here divided by each other. Negative 3 divided by negative 1 is y equals 3. Your vertical asymptote is going to be whatever makes your denominator 0. And if you're not sure, set your denominator equal to 0 and solve it. Add 1 to both sides, divide by negative 1, x is equal to negative 1. So our vertical asymptote is x equals negative 1. I'm going to go ahead and draw these in red. Y equals 3 and x equals negative 1. Once you have your asymptotes drawn in, we can go ahead and graph it using our calculator, remembering to put your parentheses around your numerator and denominator. Negative 3x plus 2 is being divided by negative x minus 1. The graph should kind of line up, and it does look like it is. It's mostly in the top left. Shift to the little top left. Let's go ahead and plot some points. We have negative 3, 5.5, negative 2, 8. That's up here somewhere. What about negative 4? Negative 4, 4.67. Looking something like that. On this side of the asymptote, what about 0? 0 is negative 2. 1 is 0.5. 2 is 1.3. And 3 is 1.75. Here is this graph with this branch. And now we just need to come up with our domain and our range. The domain, this graph, exists, does not exist at the vertical asymptote, which is at negative 1, negative infinity to negative 1, and negative 1 to infinity. The range starts at negative infinity, exists, stops existing at 3, and then picks up again at the other side of 3 and goes up forever. So it'd be negative infinity to 3, and 3 to infinity. So this has been graphing more simple rational functions. We're going to look at some more crazy rational functions. Remember, what we defined a rational function to be is a polynomial divided by another polynomial. And all the ones that we did today were, like constants or linears. We didn't look at any quadratics, any cubics, and those things are going to make the graph look significantly different. So that's what's coming. Please let me know if you guys have any questions, and good luck.